Before we dive into hexagonal architecture, I want to clarify 3 questions with you. 1. What is software architecture anyway? 2. What is the goal of a software architecture? And 3. How does the ever-popular layered architecture perform with regard to this goal? Let's start with the first question. What is software architecture? Let's assume we want to provide a web-based service. Then we have, first of all, the users who use a web browser which accesses the software via HTTP. And within the software, we have various components that communicate with each other and with external components such as a database or the interface to a third-party system. We could also provide an app. That app also communicates with the software. For that, we might need an additional component, and the app itself, of course, also has its own architecture. Architecture then is the decomposition of the software into components, the arrangement and properties of these components, and the way in which they interact with each other. What is the goal of a software architecture? A very good answer to this question was given by Robert Martin in his book Clean Architecture. The goal of a software architecture is to minimize the human resources required to build and maintain the required system. And further, if that effort is low and stays low throughout the lifetime of the system, the design is good. That sounds a bit as if it were written by a lawyer. So here's my definition. A good architecture allows software to be changed throughout its entire lifetime with consistently low effort. Effort can generally be equated with costs. Your employers or clients want to be able to change software with costs that are as low as possible and predictable in the long term. And changes, on the one hand, these are the implementation of user requirements, but even when users have no requirements, changes are often still necessary. For example, when security vulnerabilities are discovered in a third-party component, and that component has to be updated or replaced. Or when third parties changed their interfaces. I once worked on a project where we used login via Facebook, and I think every 6 months I received an email from Facebook announcing interface changes. Or when laws change. A few years ago, all companies in Europe had to adapt their software to the GDPR, the General Data Protection Regulations. So the goal must be, to use Bob Martin's words again, to keep software soft. And we achieve this by splitting the application into components that are as loosely coupled as possible and can be developed and tested independently of one another. A good example is the Internet. It consists of millions of servers that are relatively loosely coupled and that over the years and decades, independently of one another, can be modernized or replaced with a consistently manageable level of effort. How do we usually try to achieve this in software? With layered architecture. We all know it. We usually have the presentation layer with the user interface, the application layer with the business logic, and the persistence layer with, for example, a relational database and an OR mapper such as Hibernate. In many projects, however, this clean separation doesn't last very long. Often it starts with having to implement a feature under time pressure. And for that, we make an exception and access persistence directly from the presentation layer, bypassing the business logic. Or even directly access Hibernate. Or access Hibernate directly from the business logic. That is even allowed. It's called an open or non-strict layered architecture. And then at some point, we want to extend our application. Maybe we want to integrate an external system. For that, we add a client library in the logic layer and communicate with the external system exclusively via the logic layer. But then we have to implement something quickly again and, of course, only temporarily access this library directly from the presentation layer. And we also want to support an app. For that, we cleanly build a REST API that accesses only the business layer. But then there are these useful validation functions in the presentation layer that would also be very handy in the REST API. And then there's another feature that needs to be finished as quickly as possible, And making an exception once again, we bypass the business layer. And if we now also access Hibernate or the third-party client directly, nobody even notices anymore. And suddenly, not much is left of our initially clean architecture. The layer boundaries are blurred and everyone adds code wherever it seems convenient at the moment. This leads to extremely high coupling, components can no longer be tested in isolation, and we suddenly need tools like PowerMock. Using PowerMock is like painting over cracks in the foundation of your house. You're hiding fundamental flaws in the architecture instead of fixing them. And at some point, the house collapses. If we now want to upgrade Hibernate to the next major version and there are API changes, we have to adapt code in all of these layers. In one of my recent projects, a very old version of Eclipse Link was used. And for exactly this reason, we couldn't update it. We would have had to adapt all layers. That would have taken weeks, so management kept deprioritizing the update. And we could never use new JPA features. We also couldn't update many other libraries because their dependencies conflicted with those of the old Eclipse Link version. Once software looks like this, it becomes far more prone to bugs. And the effort required for fixes and changes skyrockets. And with it, the costs. Of course, it doesn't have to be that way. I'm not saying that layered architecture is fundamentally bad. I've seen many projects successfully implemented using it. But the risk is very high that an initially clean layered architecture evolves into an unclean tangled architecture like the one shown here. In a blog post published in 2005, Alistair Cockburn presented a software architecture that is intended to eliminate all these problems: hexagonal architecture. From this blog post, 3 goals can be identified. 1. The application, shown here as a hexagon, should be able to be driven equally by users, other applications, or automated tests. For the business logic, which sits at the core of the application, it should make no difference whether it is invoked, for example, by a user interface, a REST API, or a test framework. The core of the application should therefore be isolated from controlling components, from controlling infrastructure. 2. The business logic in the application core should be able to be developed and tested in isolation from the database and other infrastructure such as email delivery and third-party APIs. From the perspective of the business logic, it should make no difference whether data is stored, for example, in a relational database, a NoSQL database, or serialized in the file system. The application core should therefore also be isolated from controlled infrastructure. 3. Infrastructure components should be easy to replace. For example, an update of the database or the ORM library, adapting to changed external interfaces, or a re-implementation of the user interface. Modernizing the infrastructure should therefore be possible without changes to the business logic. This is a bit like a car where you can replace the tires or switch from winter tires to summer tires without having to replace the gearbox or the engine. These are the goals. How can hexagonal architecture achieve these goals? How does it work? This hexagon represents the core of the application. The core typically contains model classes and the business logic of the application. There are no technical details here such as REST controllers or JPA repositories. This is purely domain code. And here is the infrastructure. I initially represented the infrastructure components as question marks because when we develop the business logic, we may not yet know which infrastructure components we will need. So, how can the core communicate with the outside world? The core defines interfaces, the so-called ports. And to these ports we connect the so-called adapters. And those adapters in turn communicate with the infrastructure components. And now comes the crucial point. The business logic knows only the ports. The adapters and the infrastructure behind them are not visible to it. You can compare this to a mixing console. It has inputs to which you can connect, for example, a microphone, a keyboard, or an electric guitar, and it has outputs to which you can connect headphones, speakers, or a recording device. But how these devices work internally is irrelevant to the mixing console. And it is exactly from this analogy that the term port originates. To these ports, you can connect any device that conforms to the mechanical and electrical protocols of the port. That was quite abstract so far. So next I'll show you a very concrete example. The application is supposed to accept a user registration. For this, we define a registration port. How the application receives the registration, whether via a website, a desktop application, or a REST API, is initially irrelevant for the development of the business logic. Then the application should store the user data somewhere. For this, we define a persistence port. Where and how the data is stored is not important at first. And then we also want to send a welcome message. For this, we define a sending port. And how exactly we send the message, whether via a local or public mail server or a unified messaging provider, also does not matter from the application's point of view. To these ports, we can now connect adapters. For the registration, we can implement a website through which users can register via their web browser. We can persist the data in an SQL database. For this, we could implement a JPA adapter, for example, using Hibernate. And for sending the messages, we use our internal company mail server, which we connect via an SMTP adapter. In addition to the website, we also want to offer a REST API for registration. For this, we can simply connect to our existing port a second adapter, a REST adapter, that external applications can then access. So, what exactly happens in these ports and adapters during user registration? To explain this, I will zoom into this part. The user fills out a form in the browser and clicks Submit. The browser then sends the form data as a post request to the web adapter. The web adapter evaluates the post request and calls a registerPort.registerUser method. In the same way, an external application could send the user data as a JSON package to the REST adapter. The REST adapter evaluates the JSON package and calls the same registerUser method that the web adapter called. Let's take a look at the other side, this right-hand part. To store the user, the business logic calls a saveUser method on the persistence port. The JPA adapter generates an SQL command for this call and sends it to the database. Exactly how the JPA adapter generates the SQL, whether it uses a string builder or Hibernate or Eclipse Link, and which version of these libraries it uses, does not matter from the perspective of the application core. The core is completely isolated from the adapter. I'll show you how this isolation works in a moment. I'll zoom back out. As you may have noticed, there are two types of ports and adapters. On the left-hand side, we have those that control the application, and on the right-hand side, we have those that are controlled by the application. We call the controlling ones primary or driving ports and adapters, and we refer to the controlled ones as secondary or driven ports and adapters. Through the ports and adapters, the application core and the infrastructure are isolated from each other at this boundary. Technical details such as JPA, Hibernate, REST or JSON are only visible in the adapters, not in the application core. The core does not know which technologies and libraries we use around it, and it does not matter to it either. This is like the mixing console we mentioned earlier, and for example, the electric guitar. For the mixing console, it doesn't matter what material the guitar is made of, which strings are mounted on it, or who is playing it. Now, today I've used the word isolation many times. Isolation, that sounds good, And it can also be illustrated nicely in these pictures. But how does it work in practice? How can isolation be realized in software, in code? I'd like to show you this using a class diagram. This is our application hexagon, and inside we have the implementation of user registration in the register user service. We also define the public interface of this service in an interface, the register user port. And the service implements this interface. This interface is then accessed by a REST controller. And this controller then uses, for example, REST Easy. If we now split the code into two modules, for example, two Maven modules, then we have an application module here and a controller module here. The controller module has dependencies on the application module and on REST Easy. And since the dependency goes from the controller to the application and not the other way around, the application module also has no dependency on REST Easy. So the code in the application module knows nothing about the technology used in the controller module. On the other side, we have the JPA adapter with a dependency on Hibernate. So how can the application code in the register user service call the JPA adapter? If we set up a dependency here, then the application module would also have a transitive dependency on Hibernate. And with that, not only the application module, but also the controller module. And it's exactly this chain reaction of dependencies that we want to avoid with hexagonal architecture. We do want to, from the inside, call code out there, but we don't want a dependency in that direction. And that's why we turn the dependency around. We invert it using the dependency inversion principle, the D in Solid. And it works like this. We add another interface to the application hexagon, the persistence port. The service has a dependency on the interface, and the JPA adapter implements the interface and is connected to the service via dependency injection. As a result, the call goes from inside to outside, but the source code dependency goes from outside to inside. And this means the application core has no dependency on the JPA adapter and also no indirect dependency on Hibernate. So the core has no knowledge of any technical details. It knows neither REST Easy nor JPA or Hibernate. All these technical details exist exclusively outside the core in the adapters. All dependencies point from the outside toward the application core. This is a fundamental principle of hexagonal architecture, and it also has a name, Dependency Rule. The Dependency Rule states that all source code dependencies must be directed from the outside toward the application core. And in this way, the Dependency Rule is like a protective shield for the application core. It shields the core from all technical influences from the outside. Here you can see the overall architecture again. All dependencies lead to the core. And this enables the isolation that makes hexagonal architecture so powerful. But it also requires more work, and that brings us to the topic of mapping. When we work with the JPA, our user class usually looks something like this. It has annotated fields and corresponding dependencies to JPA. So where do we put this class? Let's take another look at the class diagram, and now let's zoom into this right-hand part. If we place our user class here in the application core, then for the annotations, we need a dependency from the core to Hibernate. But we have just removed that dependency by applying dependency inversion. And we learned that the dependency rule, one of the fundamental principles of hexagonal architecture, explicitly does not allow this. If we move the user class into the adapter module, then the dependency on Hibernate is inside the adapter. But the register user service also needs to know the user class, and that means we have violated the dependency rule again. To resolve this dilemma, there are several mapping strategies. At this point, I will present just one of these strategies, which in my experience is usually the most sensible one, namely two-way mapping. At the end of the presentation, you'll find a link to an article in which I also describe some other mapping strategies. With two-way mapping, there are two user classes. One in the application core and one in the adapter, which is now called JPA user to avoid confusion with the user class in the core. The JPA user class looks like this, essentially like the user class I showed earlier. It has annotated fields, dependencies on JPA, and usually getters and setters. The user class in the core, on the other hand, looks like this. It has similar fields, but no JPA annotations. Instead, for example, it has a constructor that validates the parameters and then creates a new valid user object with the required fields such as the registration date shown here. So it contains only purely domain-related concerns. And if we work with a rich domain model, then this class also has methods that allow us to change the state of the user object. So we have these two user classes, and now it is the responsibility of the JPA adapter, when the save user method is called, to map the user object from the application model to a JPA user object and then persist it via Hibernate. The JPA adapter, of course, also has a load user method, which loads a JPA user via Hibernate, maps it to an application user object, and returns it to the calling code in the core. In code, this looks something like this. Here's the save method, which maps the user object to a JPA user object and persists it, for example, via a Spring Data repository. And the load method looks like this. It loads the JPA user object via the Spring Data repository and maps it to a user object, or rather to an optional of it. You don't have to implement this mapper yourself. There are libraries for this, such as MapStruct and Model Mapper. If you Google it, you'll find a few others like JMapper, Dozer, and Orica, but those have not been actively developed for a while. Such mapping is not only useful for the JPA adapter, but also for the REST adapter. So let's zoom into this area. Here's our user class, and often we don't want to expose all attributes of an entity through the REST API. In the case of the user class, for example, we might want to hide an internal nodes field or the ID of the person who created those nodes. In addition, for date and time fields, we need to define how they should be formatted in the JSON payload. A user class for the REST controller might look like this, for example. It uses a JSON annotation to format the timestamp and therefore has a dependency, for example, on Jackson. And we don't want this technical dependency in the application core either. So here's again the class diagram. So we placed the user DTO together with a JSON library outside the core in the controller module. And the REST controller now maps in the register user method the user DTO to a user object. And the controller, of course, also has a get user method, and in that it maps the user object from the application core to a user DTO. By the way, such mapping is not only useful in hexagonal architecture, layered architecture can also benefit from it. But in hexagonal architecture, it is absolutely necessary in order to keep technical details out of the core, while at the same time not violating the dependency rule. And now we come to one of the big advantages of hexagonal architecture, testability. At the beginning, I talked about the goals of a software architecture. And there I mentioned isolated testable components as one of the requirements. And in fact, hexagonal architecture makes it very easy to test components in isolation. We can easily test the application core by invoking it via a primary port and connecting the secondary port or ports affected by the test with test doubles. The test double, in the role of a spy, records the calls coming from the core. And in the role of a stub, it simulates responses from the adapter. The test then verifies the response of the application core and the recorded interaction with the adapter. We can not only test the business logic in isolation from the adapters, but also, conversely, test the adapters in isolation from the business logic. Here's our REST adapter. We can test it, for example, using REST assured. This sends an HTTP request to the adapter, and the REST adapter then calls a test double of the primary port. The test double again should record the calls and simulate a response from the application core. And the adapter then sends a response back to the test. And there once again the response can be verified along with the interaction with the application core. Here is the JPA adapter. Here we can, from our test, start a database using test containers and populate it with test data. Then the test calls the adapter and the adapter sends an SQL query to the database. The database sends its response to the JPA adapter and the adapter sends a response to the test. In the test we can again verify the response and the expected changes in the database. In addition to these integration tests, we should of course, independently of the architecture, also write end-to-end tests. If we take another look at the entire application, then all these components can be tested in isolation from each other. Just as an electric guitar, keyboard, microphone, mixing console, headphones, speaker and recorder can also be tested independently of one another. Alistair Cockburn was asked in an interview, why a hexagon actually? Does it have any special meaning? And Cockburn's answer was surprisingly pragmatic. He wanted to use a shape that no one had used before. Rectangles are used everywhere, pentagons are hard to draw, so it became a hexagon. Another question that is often asked is, what is the difference between hexagonal architecture and ports and adapters? The answer is very simple, there is none. Both terms refer to the same architecture. The official name that Alistair Cockburn gave to his architecture is ports and adapters. The term hexagonal architecture comes from the graphical representation that you have seen many times today. In the interview I just mentioned, and to which I will give you the link later, Alistair Cockburn revealed that he himself also prefers the visual name, that is hexagonal architecture, but that the official name of an architecture must be one that describes its properties. And ports and adapters does that better than hexagonal architecture. And with that, we have looked at the hexagonal architecture or the ports and adapters architecture from all sides. We have the application core with the business logic and without any technical details. We have ports which in code are simply interfaces. We have adapters which contain the technical details and which we connect to these ports. Primary adapters call primary ports. Secondary adapters, on the other hand, implement secondary ports. We have the infrastructure with which the adapters communicate. And we have our shield, the dependency rule, which defines that all dependencies must point toward the core. And now I would like to remind us of the goals of a software architecture and compare to what extent hexagonal architecture fulfills these goals. Here are the goals again. Software should be easy to change, and it should remain so throughout its entire lifetime. We achieve this by structuring it into loosely coupled components that can be developed and tested independently. Let's go through the criteria one by one. Changeability. We can change the business logic at the core of our application without having to change the adapters or the infrastructure, as long as we keep the ports unchanged. In practice, of course, a change in business logic often also comes with changes to the user interface and the data, so admittedly this is not the killer argument. Much more important is that we can update or completely replace the adapters and also the libraries they use, such as REST-easy, Jackson, Hibernate, etc., as well as the infrastructure components like the database, without having to change a single line of code in the business logic. If we here want to upgrade Hibernate to the next major version and that upgrade requires code changes, then only the JPA adapter is affected because it is the only component that has a dependency on Hibernate. To pick up the car analogy again, if you want to change your tires, you might need different rims, but you don't need a new axle, a new transmission, or a new engine. At the end of the presentation, I'll link an article series in which I demonstrate that even the application framework can be a replaceable technical detail of the infrastructure. In that series, I replace Spring with Quarkus without changing a single line of code in the application core. Another major advantage that I also categorize under changeability is the following. You can start by developing the application core and initially define only the interfaces for the ports and test against them without having to worry about the adapters or the technology you will use behind them, whether REST or GraphQL, whether Spring Data or Panache, or whether SQL or NoSQL. This allows you to postpone decisions about infrastructure technologies until you have gained enough experience with your application during the development of the business logic to make much better decisions about which technologies are best suited. For example, what kind of database is best for storing your data. Let's move on to the second point, loose coupling. We achieve loose coupling first of all quite clearly through ports and adapters. And secondly, by splitting the components into separate modules such as Maven modules. Business-related topics are implemented exclusively in the application module, and all technical topics are implemented in one or more adapter modules. We define the dependencies between the modules according to the dependency rule. This ensures that no technical dependencies leak into the core and that we can clearly localize all responsibilities in the code. Because now, when creating a new class, we have to think very carefully about which module it belongs to. If we put it into the wrong module, we will either not be able to access the code we want to call from there, or we won't be able to access the new class from the code that is supposed to call it. And this exact just quickly attaching new code somewhere is something that layered architectures with their countless transitive dependencies unfortunately strongly encourage. The third point is independent development. Once the application core with its ports has been defined, further work on the components can easily be split, for example across multiple pairs. And fourth, independent testability. I showed this just a few minutes ago. By using test doubles, we can test all components completely in isolation from each other. Hexagonal architecture therefore fulfills all the criteria of a good software architecture. So, should you only work with hexagonal architecture from now on? No. Hexagonal architecture, of course, also has a downside. You don't need to read this. This is a screenshot from my IDE from a project with one application module, 3 adapter modules, and a separate model module and a bootstrap module. And the ports could also be placed in a separate module. Splitting the code into modules, implementing the ports and the adapters and the mapping represents a huge amount of additional effort. If in the end each of these modules contains only a single class, for example in a simple microservice that writes a single entity to the database and reads it back, then this additional effort is not worth it. But for a large enterprise application, where each of these modules later contains hundreds of classes, the effort can pay off quickly, and you can save effort and cost in the long term. It's good if you have someone on the team who already has some experience with hexagonal architecture and who can assess whether this additional effort is worthwhile for your project. Or even better, develop a small application yourself using hexagonal architecture, gain some initial experience, And then you can be the person who brings hexagonal architecture into play in your next project. And with that, we've reached the end. Behind the QR code, you'll find the promised links and the slides. And if you're interested in more content from me, less about architecture, more about new Java features, feel free to check out Happy Coders EU or one of the other channels. Thank you for your attention.